Good morning. Today I want to continue on with our discussion of Chapter 21. And today we're going to look at what causes certain nuclei to be radioactive. Maybe a little bit about ways we detect that radioactivity. And we're going to close this section by looking at the kinetics of radioactivity. So first of all, in the last section, right, we talked about the modes of decay. Right? What do they do? What do these nuclei do? And we talked a little bit about why one nuclei might undergo one type of decay, but another nuclei might undergo a different type of decay. And we're going to get into a little bit more of that in today's class. So, first of all, the nucleus itself, right? The nucleus is held together by something called the nuclear strong force, right? This is what binds the particles within the nucleus together, right? So it's this nuclear strong force that's responsible for holding the particles of the nucleus together, right? It is a strong force, but it's not a very expansive force. So it only operates over very short distances, right, within the nucleus, right? So it holds those nuclear particles together. Little bit of vocabulary, right? You might hear the term nucleons, right? A nucleon is a nuclear particle. So a proton and a neutron, right, are the nucleons. So we talk about the number of nucleons in the nucleus or the nuclide. Now, it's long been believed that neutrons essentially play the role of stabilizing the nucleus, or they act like glue to hold the protons together, right? Because if we think about the protons, right, they are positively charged, and we've talked a lot about how like charges repel each other. So there's a very big, driving force for these protons to want to get away from each other. And we believe the nucleus, the neutrons, acting with the strong nuclear force, or what hold those protons together, right, which hold the nucleus together. They don't add to the strong force, right? Only the protons do. So we believe that they act as that stabilizing ability, because they give us more force, but they don't want to get away from each other. Now, our biggest way, or the simplest way that we can look at this, is to look at what's called the N to Z ratio. So this is simply put the ratio of the neutrons to the protons in the nucleus. And as we'll see, depending on the size of that nucleus, we would want a particular ratio to keep it stable, right? Or if we can look at stable nucleuses versus unstable nucleus, we can see that we want certain ratios of neutrons to protons. So of course, if the N to Z ratio is too high, right, in other words, we have too many neutrons for the number of protons that we have, we're likely to undergo beta decay, right? Because remember, beta decay effectively turns a neutron into a proton. And so this will lower my N to Z ratio. So beta decay lowers N to Z ratio. Now, if the N to Z ratio is too low, meaning there's not enough neutrons for the number of protons, then we can undergo either positron emission or electron capture are the two processes that will change that ratio to make it higher, right? Increase the number of neutrons by lowering the number of protons, right? So protons are effectively converted to neutrons in both of these processes. Now, of course, alpha decay can do this as well, but not nearly as efficiently because we're losing both 2 neutrons and 2 protons. But what we'll see is as you go to lower mass, you don't need as high a ratio. So by lowering the mass, you're lowering the needed ratio, and so even though a single alpha decay doesn't change the ratio because you lose 2 and 2, right? It lowers, by lowering the mass, you're lowering the ratio that you need. So you're going to get to an appropriate N to Z ratio by alpha decay, but not nearly as efficiently as positron and electron capture. So what do we need the N to Z ratio to be? Well, this is what comes in when we talk about the valley, or sometimes called the belt of stability. So let's look at our graph here. So first of all, the red line here represents an N to Z ratio of 1. So that's kind of our reference point, right? Now, if we look at the graph here, and I'll blow it up here for a second, you can see it. All of the yellow nuclei here, the yellow dots, represent unstable nuclei, right? Radioactive nuclei. The green dots here represent stable or non-radioactive nuclei. So a couple of things here. There are radioactive nuclei all along the spectrum of small nuclei, big nuclei, right? Atomic numbers, big, small atomic numbers, etc., right? So almost all elements might have a particular isotope that's radioactive. Now, that isotope may be found in very small quantities, or it's a very low natural abundance, but even hydrogen has radioactive isotopes. And so they're not isolated so we might think of very big nuclei, because we think of things like uranium and these big atoms that are radioactive. There's radioactive isotopes all throughout the mass spectrum of elements. So the other thing to point out is we have this sort of belt, or what we call the valley of stability, that kind of runs along or in the middle of all of these unstable. So there's unstable both above and below this valley of stability. So as we trace this, what we see is the N to Z ratio that we need, right, if we track that belt, becomes higher and higher as we get to more and more protons, right? So if we increase the number of protons, we need more neutrons to stabilize them. So it begins in the early elements, so basically from 1 to 20 protons, or if you're thinking about elements, right, in the elements leading up to calcium, right, the first 20 elements, you want about a 1-to-1 N to Z ratio. So 1 proton to 1 neutron. And we can see that here in the graph. As you get more and more protons, you need more and more neutrons to stabilize them. So over the next sort of 20 atoms leading up to through like zirconium, you have a ratio of about 1.25 neutrons for every proton. So you need another neutron for every 4 protons that you have, if you will. And so we can see this stability gradually drift away from that 1-to-1 ratio. As you get to even higher, so elements 40 up to 80, so all the way up to tantalum or mercury and into that range, lead, right? You work your way up to needing a ratio of about 1.5 neutrons for every proton. Now, the other thing to notice, right, is there's a cutoff here. So if you look here, there's a point beyond which there's no more green dots. There's no more stability. So the heaviest element that has stable, non-radioactive nuclei is lead. Atomic number 82. Anything that is greater than 83, or the number 83, right, is going to be radioactive, right? And so anything above that number is going to have that radioactivity associated with it. Okay, so that sort of spells out where are we at? And I misspoke a minute ago, sorry. Lead is the one that we usually think of. Bismuth is actually the heaviest element that has stable nuclei, right, at 83. So lead is 82, bismuth is 83. We think about lead being a stable because it is the product of a lot of nuclear decays, right, getting to lead. So now that we have sort of what we want, now we can start to look at, oh, if we have this isotope, how might it become stable? So if we look at our chart, right, we have Z on the bottom, N on the y-axis. So if we have, for example, an element here, right, it has too many neutrons, right? So for the number of protons, right, in order to be stable, it would have to drop down to have fewer neutrons. So we would want to undergo a decay process that would give us more neutrons, or excuse me, less neutrons for the number of protons, right? So the only way that, or one of the ways that we can do that, of course, is to lower the number of neutrons is beta decay, right? So things that tend to be above the belt will likely to undergo beta decay, because that's going to cause a neutron to go and a proton to become. So we don't actually drop straight down, we drop a little diagonally, right? So we drop down, but we shift a little bit over, and so we keep doing this sort of dance where we go until we were to get to a stable isotope or a stable nuclide. If we find ourselves below the belt, so essentially we need to get more neutrons, then this is where we would start to see positron emission, electron capture, which would decrease, right? Which would send us sort of up the staircase, right? So they're going to decrease the number of protons, increase the neutron. So you're going to make these kind of climbs until you end up at a stable nuclide. So this is the idea. Now, of course, all of these processes can undergo alpha decay as well, you know, as a means to drop down the mass. Now, what I will point out is atoms up here will definitely undergo alpha decay, potentially, probably along with other forms of decay as well, to drop down the mass, right? Because you're not going to get, you know, simple beta decay or electron capture, positron emission are not going to get you to very efficiently to something that's stable. So we get down to a mass that's more stable, then we might need to undergo other kinds of decay process to get us to an actual stable nuclide. So a lot of times nucleuses don't just simply undergo one kind of decay. They might undergo a decay, but it doesn't give you a stable nuclei. So it undergoes a different decay or another decay. And so it's a process of multiple decays to get to a stable nucleus. Now, there are other things that people look at when they think about stability of these. Now, I'm not going to spend a lot of time on this, but there's some trends that have been seen, so-called magic numbers or different things that seem to be true among stable, when we think about stable nucleuses. And that is the actual numbers of protons and neutrons. So what we've seen is that a large number of stable nuclei have an even number of protons and neutrons. There seems to be something about having an even number of protons and even number of neutrons that gives you a very large number of our stable nuclei. So if these are how many stable nuclei there are, or stable isotopes that there are, 157 out of, say 270-ish nuclei have both even protons and neutrons. Only 5 stable nuclei have both being odd, right? And you can see about equal numbers have one even, one odd. And so there seems to be something special about having both even protons and neutrons. We've also seen combination numbers, right? So if the total number of nucleons add up to a so-called magic number, the nucleus seems to be more stable. Maybe this operates in the same way that having the right number of electrons stabilizes noble gases, and there's a pattern there. We don't actually know, or at least we don't definitively know, but there's evidence supporting these. So if N or Z is either 2, now this is not, again, the sum of them, this is just if N or Z equals 2, 8, 20, 28, 50, or 82, they tend to be more stable. Or if N equals 126, there is no Z 126, right? There's no atom that heavy, then these tend to be more stable. So this is the idea of magic numbers. Don't want to dwell on this too much. Just the basic idea is that there seems to be other factors besides specifically the N to Z ratio that can influence the stability, such as having even neutrons and protons. Now, as I mentioned, many heavy atoms will undergo processes of decay. So what we call a decay series. And these are nice and easy to track. We can predict, if we go through a little bit of a process, we can predict how many alpha, how many beta are necessary for a particular isotope to undergo decay. But what this does is it gives us the idea that one decay is not enough, right, for these heavy atoms. And so uranium, for example, we saw it undergo an alpha decay to get to thorium-234. Right? Thorium-234 is not stable, right? And so we undergo other decays. So as we trace this, right, so thorium undergoes a couple alpha decays to get back to a uranium-234. Again, not stable yet. Then we see beta decays, getting down to a different thorium isotope, and then a radium isotope, then a radon isotope. Again, all unstable, right? Radon has an 86 atomic number, so we're still not where we're going to have any sort of stability. And then down to polonium-218. Again, not stable. We get down to we get to an isotope of lead, right? One of the heavier stable nuclei. But this isotope of lead, not necessarily stable because of the N to Z ratio. So what we see is different decay processes, right? We have series of alphas and betas that ultimately get us down to a different isotope of lead, lead-206, right? Which is a stable isotope of lead, right? A non-radioactive isotope. So we're going to go through these series of decays until we get to a non-radioactive nuclide. So we'll come back to that a little bit later and talk about it. I'll do an example problem in a second here dealing with this. But first, I want to talk just a little bit about detecting radiation. And so there's a couple basic ways that radioactivity is detected. One is something very simple called a thermoluminescent dosimeter. And this is simply where those particles emitted by radioactive nuclei, the alphas, the betas, have a lot of energy, and therefore they can be detected. And so what these dosimeters have are salts that are excited by the ionizing radiation. So these contain certain salts, ionic compounds, that are ionized by this radiation. When they are exposed to radioactivity, the crystals become warmer. Right? The excited electrons relax back down to their ground state, emitting light, and the amount of light is proportional to the radioactive exposure. So what happens is somebody wears this dosimeter. After a certain period of time, the dosimeter is tested by heating it up. They can look at the light that's emitted upon heating, and they can then tell how much radiation that crystal had been, or that ionic compound had been exposed to. So this is a type of rad badge, if you will, right? That you think about somebody wearing to measure radioactive exposure. These aren't going to tell you immediately that you're being exposed, but if it's tested, they can tell you that there's been an exposure. So typically these are on some sort of testing cycle where either they're tested under a normal amount of time, or if you both believe there's been an exposure, you could do a test to tell whether there has been an exposure. Probably the most well-known form of radioactivity detecting is what's called a Geiger counter, or a Geiger-Müller counter, where the radioactive particles, or the radioactive particles and rays cause air to be ionized. And so what you're holding this wand here, and if as the radioactive particles enter into that wand, they ionize particles inside here, typically argon particles, right? Creating argon ions. Those ions are then detected in a battery, if you will, right? We have an electrical circuit in here which causes the detection of this. So the argon ions are attracted, and that creates an electric current, and that current is registered on the meter or the counter, and we get that characteristic needle moving, often accompanied by some sort of audible indication, which we associate with the Geiger counter, that clicking, right? That's telling us the ionization is occurring, right? That clicking is an indication of the electrical current flowing through the circuit. So the circuit is completed by the creation of the charged particles. Of course, the more clicking, right, the more current, the more ionized, the more ions that are being created, the more exposure to the radioactive particles. Okay, so now I want to do a couple of sample problems. The first problem here is predicting, based on the N to Z ratio, whether something will undergo beta decay or positron emission. So let's look at our first example, lead-192. So the way that we can look at this is, first we need to establish what the N to Z ratio is. So we know that the mass number is 192. We know that Z for lead equals 82. So that means the number of neutrons is going to be 192 minus 82, or 110. So my N to Z ratio equals 110 divided by 82. So if we plug that into our calculator, we get 1.34. Now, we know that elements with 80 protons, or in that range, right? They would like N to Z to be about 1.5. So N to Z is too low. So in order to raise N to Z ratio, right, to create a neutron at the expense of a proton, that's going to be done by positron emission of these choices. Right? So positron emission is one of the things that can happen if our N to Z ratio is too low, right? Because that'll create neutrons at the expense of protons. Raise the top number, lower the bottom number, if you will. So now let's do the same thing with, this should be PB212. The PB212. So again, we know that Z is equal to 82. In this case, N is equal to 212 minus 82, or 130. So that means my N to Z ratio is 130 divided by 82, or 1.59. So this might actually be a little too high for lead, right? If we had to pick one, right? We'd like it to be about 1.5 for lead. So if I need to lower, right? So this is too high. So to lower it, we got beta decay to lower N to Z. So it's really by looking at the number of neutrons and protons, looking at, then calculating the N to Z ratio, and looking at, based on the atomic number, right, based on the number of protons, what kind of N to Z ratio do we want, and then making a prediction based on that, which mechanism of decay is going to get you there. Okay. The second problem here I want to do is to look at one of these decay series problems and see how we can come to a prediction or predict on a certain decay series how many alpha and betas were involved. So let's say that this uranium-238 isotope decays to lead-206. And we want to know how many alpha and beta decays occurred. So what we need to do is look at what changes occurred, first of all, right? So the first thing here is to think about what changes occurred to the mass number and the atomic number. So first of all, the mass number went down from 238 to 206. So the mass number decreased by 32. The atomic number went from 92 to 82, or went down by 10. So if we turn our attention to, first of all, the alpha particles. So the only thing here that is going to, because they're the only thing that's going to change the mass number, right? Remember, beta decays don't change mass. So all of this mass number change has to occur via the alpha particles. So remember, an alpha particle looks like that. So an alpha particle changes the mass by 4. So how many alpha particles would have to be necessary to change the mass by 32? So if we simply do 32 divided by 4, we get 8. And so what I know is there's going to be 8 alpha decays in this series. Okay. So now what about the beta? So the same alpha decays, right, they not only lower the mass number, by 32, they also lower the atomic number by 2 each time. So they're going to lower the atomic number by 16. Okay, so they're going to take the atomic number from 92 minus 16 or down to 76. Well, we need it to go to 82. So what do the beta decays do? Well, the beta decay, remember, that's going to raise the atomic number, right? So a beta decay will take away a neutron, change it into a proton. So determine the number of betas, we can simply do, 76 plus x to get me to 82. So x equals 6. So I need 6 beta decay. So in order to accomplish this decay series, I need 8 alpha decays to bring down my mass number. That will lower my atomic number by 6 too many, right? So I need 6 beta decays to bring my atomic number back up to where it is in my product, my daughter nuclide. So in this way I can predict the decay series. Okay, so today I want to close out today's section by talking about the kinetics of radioactive decay. So this is going to bring us back to topics that we talked about much earlier in the semester when we were talking about kinetics, right? So if you remember back to chapter 15, when we talked about kinetics, might be some information there you want to review as we go through or understand the kinetics of radioactive decay. So specifically the kinetics that we're looking at are the rate of change in the amount of radioactivity in these nuclei. So what do we know about this? Well, we know that the amount of radioactivity is constant and is different for each isotope. So we know that there's a constant change, so we have fairly constant kinetics, right? And it's different for each radioactive isotope. We also know that each radionuclide, right? Each radioactive isotope has a particular length it requires to lose half of its radioactivity. Remember what we called the half-life. And it's a constant half-life, right? So it takes the same amount of time to lose the first half, to go to 50%, and then go from 50 to 25, etc. And as we remember, that's indicative of first-order kinetics. So radioactive decay follows first-order kinetics. So we're going to use the first-order kinetics equations that we talked about back in chapter 15, maybe with a little different symbolism, to look at radioactivity or the kinetics of radioactive decay. Now, should point out a couple differences, right? Unlike chemical reactions, the rate of radioactive change is not affected by temperature, right? So we saw that the kinetics can be affected by temperature. So if we heat something up, it could speed up the kinetics, etc. That is not true with radioactive decay, right? Doesn't matter if it's very hot, right? The kinetics will stay the same. So let's look at the basic equation. So if we remember back, our basic kinetics equation is the rate equals the rate constant times, for radioactive decay, the number of radioactive nuclei. So this is our first order rate law. Right? In chapter 15, right, instead of N here, we had the concentration. So we have rate equals this rate constant times the number of radioactive nuclei. And of course, our half-life equation is going to be the first order half-life equation, right, which equals 0.693 divided by the rate constant. So just to refresh our memories, right, what does this mean? Well, it means, for example, that if thorium-232 has a half-life of 14 billion years, and we had 1 million thorium atoms, thorium-232 atoms, then after 14 billion years, we'd have half a million. After another 14 billion years or 28 billion years, we'd be down to 250,000 of thorium. Now, one of the take-home messages of this is if we have some of these radioactive isotopes have huge half-lives, right? And what this tells me is it can take a long time for some of these radioactive nuclei to disappear, right? So if we're creating these by some process, then they're going to be around for a long time potentially. Now, of course, there are radioactive nuclei that have extremely short half-lives, right? Fractions of a second. Now, in sort of the language of radioactivity, the shorter the half-life, the hotter the sample, right? So we say something that's a really hot radioactive sample. A lot of times what that means is we have radioactive nuclei in there that have very fast half-lives. They're giving off a lot of radioactivity, a lot of radioactive particles, alpha particles, beta particles, gamma rays, right, in a short period of time. They're undergoing a lot of decays in a short period of time. So just to give a survey here of a few nuclei, right, in a range of half-lives, we talked about thorium-232 has about 14 billion years, 1.4 times 10 to the 10th years. These are alpha decays, or at least that's the major decay process. Uranium-238, right, one of the radioactive uranium nuclei has about, 4.5 billion years half-life. Other ones that maybe we'll look at, like carbon-14, right, used in carbon dating that we'll talk about in just a few minutes, has a half-life of about 5,700 years. You'll see different numbers bandied about in problems, 5,715, 5,730, right around 5,700 years. That's a beta decay typically, or beta process. We have radon, right? Radon is particularly important because it's a radioactive gas, and we find it in basements sometimes in this part of the country. It has an extremely short half-life, right? 55.6 seconds. So what we can see is that there's a range of half-lives, right? And it's not always by what nucleus it is, right? There's another isotope of thorium that has a half-life that is fractions of a second. So there's a huge range. Some are hugely long, billions of years. Others are fractions of a second. But what they all have in common is that they decay via first-order kinetics, a constant half-life. So while it took 28 billion years for 1 million thorium-232 atoms to drop down to 250,000, if we had radon-220, right, with a half-life of a minute, essentially, then if we start off with 1 million, we'll be down to essentially of 250,000 within 2 seconds. So hugely different kinetics in terms of how long it takes that radioactive isotope to drop down or to disappear. Now, if we're just going to start to do some calculations here, we need to lay out some equations. So, we look at the integrated rate law for first order decay. Now, this is the integrated rate law. Now, we've also seen other versions of that integrated rate law back when we did normal kinetics, where we got rid of the fraction here. But for radioactive kinetics, this is the most useful because we'll often be comparing the number of radioactive particles at the beginning and the end, right? So at time 0 and some passive time. So this is often a very useful version of the equation to use. Now, potentially we could use a different version of the integrated rate law, but this is the one that we typically start with. So remember, this is the first order integrated rate law. Now, as I said, this is sometimes, or a lot of times, the number of actual nuclei. It could also be rates of decay, right? Which is just another way to look at the number, because the rate of decay will change over time, right? As we start out, we have very fast decay because we have a lot of radioactive nuclei. As that number drops down, the rate goes down, like we saw in first order kinetics, where we would substitute in here the rate at time t over the initial rate. So these could be actual numbers, they could be rates, are some of the common things that we have ratios of. So one of the big applications of this is so-called radiocarbon dating. So this is where we're using a particular decay process, and that is the decay of carbon-14. Now, that carbon-14 is ultimately decaying, and I'll draw it here. You'll see it, I think, later on in a slide. But we have carbon-14 decaying down to a nitrogen isotope via, again, beta decay. So this is premised on the idea that all living things, or all things that were or are living, contained carbon. Right? And there are 3 isotopes of carbon. Carbon-12, carbon-13, carbon-14. Carbon-14 is a radioactive isotope. Has a half-life, again, numbers ranging from 5,715 to 5,730 years, depending on the source you look at. Now, one of the things we do know is in the atmosphere, carbon-14 is produced at a fairly constant rate. And so, by the process that looks very much like the reverse of what we have here, where nitrogen 14(7) gets bombarded with a neutron to produce, oops, all right, make my notation right here, bombarded with a neutron to give a carbon-14 and a hydrogen atom, or a hydrogen nuclei. Oops. 6. So what this is saying is that we keep producing carbon-14 at nearly the same rate that it decays. So the atmospheric concentration, and therefore the concentration in living organisms is constant. Right? So, but when an organism dies, that amount of carbon-14 will then start to drop down because it's no longer absorbing or incorporating more from the atmosphere. Right? So, here's sort of the basic premises. So while we're living, or while things are living, we have a constant carbon-14 to carbon-12 ratio because the organism replenishes its supply of carbon. Now, most of this comes from carbon dioxide in the air to that organism. Now, once the organism dies, that ratio starts to decrease because the carbon-14 goes down, but the carbon-12 doesn't. So we start to lower this ratio. And again, we have the half-life, which tells us the rate at which that lowering occurs. And so by measuring the carbon-14 to carbon-12 ratio in that once living material, right, in the thing that you're trying to figure out how old it is, and comparing it to what the carbon-14 to carbon-12 ratio in a living organism is, we can tell how long ago that organism was alive. Now, radiocarbon dating, or so-called carbon dating, is limited to about things that are about 50,000 years old. And the basic idea here is that 50,000 years represents about 9 half-lives in terms of carbon-14 decay. And at that point, we're down to so much, or to such a little amount of carbon-14 that's left that we can't really measure accurately anymore. And so, after about 50,000 years old, the amount of carbon-14 present is way below what we can measure, the so-called background radiation. So the aging, or how we can date things, limits to things that are, 50,000 years old or younger. Now, if we want to date things that are older, right, there are other methods that we can use. We have so-called radiometric dating, right? Not radiocarbon dating, radiometric dating, which uses different techniques, but one of the more common ones is looking at the decay of uranium-238 to lead-206, right? That decay series that we looked at before, that occurs in igneous rocks, or rocks that come from volcanic sources, right? So the half-life for the decay of uranium-238 is about 4.5 billion years. So what we can compare the amount of uranium-238 to that of lead-206 in these volcanic rocks and or meteorites, right? And we can age them, right? Now, by doing this dating process, right, the Earth's age is estimated at between 4 to 4.5 billion years, right? And this agrees by both the uranium-lead dating and also another type of radiometric dating, which looks at the decay of potassium-40 down to argon-40. Now, how do we come up with this age? Well, the oldest rocks tested on Earth, right, have been dated to about 4 billion years old, right? So that sort of gives us what we call the lower limit, right? We know it's at least 4 billion years old, right? The Earth is at least as old as the rocks that are here, right? Now, they've also dated about 70 meteorites that have struck the Earth, right, externally, and those have been found to be about 4.5 billion years old. And so, believe that these meteorites were formed at the same time that the solar system, which included Earth. So, the best estimate to when Earth was formed is about 4.5 billion years ago. So this radiometric dating is useful in a lot of ways. Now, this radiometric dating can also tell us things like fossils, right? Now, we talk about aging fossils, but fossils are not living, right? Or they never were, right? Fossils are imprints from living is. So what if we don't have the actual bones? We just have the fossils, right? Well, what they do is they can date rocks that are in the same level of sediment, right? Using radiometric dating to see how old those rocks are. So if there are igneous rocks in the same region or near the same, sort of level of soil where these fossils were dug up, then we can have a fairly good way to date things, thinking that the fossils were formed at about the same time that these igneous rocks were deposited, giving us a good estimate of the age of these fossils. All right, so I want to close out this section, or this class, by looking at a couple of sample problems, looking at the kinetics of radioactive decay. So with a lot of these problems, we look at example techniques. So a lot of the problems will involve things like radiocarbon dating. But we'll do a second problem here that just involves normal radioactive decay. So we'll do an application problem, and then we'll look at just a normal nuclear decay problem. So in this particular problem, we says that a scroll, is believed to be from 500 BC. Its carbon-14 decay rate is 89% of that found in living organisms. How old is the scroll? Now, our go-to equation here, of course, is our integrated rate law. Now, I chose this problem because it's not as obvious what we plug in for the rate of t and the rate 0. Right? So some problems will give you the actual decay rates, right? They'll say the rate of decay is 4.5 disintegrations per second. The normal rate of decay in living is, say, 15.3 decays per second. And then you have numbers to put in here, right? You have the initial rate and the rate at some time t. But they don't tell you that here. They just say the decay rate is 89%. So we have to kind of figure out what we might use to represent that. So the easiest way to do this is to understand that the rate at time t we could call 89, or if you prefer, you could call it 0.89. And the rate at 0, right, of course, at the initial rate, the rate is 100%, or 1. So it doesn't matter which one you use, it's a ratio, so you're going to get the same idea. So what we can then do is we can have the ln of 0.89 over 1 equals negative kt. Okay. Well, before we complete that problem, we have to know k. Now, just like we saw with normal kinetics problem, the basic way or the easiest way to get k for first order kinetics is to do the half-life equation. So if we use the half-life that's typically given in the book here, which is 5,715 years, as the half-life, then we can calculate k. Remember, k for first order kinetics equals 0.693 over the half-life, 5,715 years. And so k here equals 1.213 times 10 to the negative fourth reciprocal years. Okay, so we have our K. So now we can plug this in. So I'm going to rewrite this in as the natural log of 0.89, right? 0.89 divided by 1 equals negative 1.213 times 10 to the negative fourth times t, right? Our time. That's what we're ultimately trying to get to. So if we start doing some math here, some simplification. So when we simplify here, we get negative 0.1165, let's say, equals negative 1.213 times 10 to the minus fourth t. So if we do our division, t equals negative 0.1165 divided by negative 1.213 times 10 to the minus fourth. So if we do that, we get a T of 960 years. So some of our units there are reciprocal years. So 960 years, or 961, depending on your rounding. So to answer the question, that's not necessarily directly posed here, but is this scroll from 500 BC? Well, if we think about 500 BC, that would be approximately, so if we think about, if we just say 2000, right? 2020, it's 500 years before Christ, so that's approximately 2,500 years ago. And so this scroll is only dated at 960 years ago, so there's no way that this scroll is from 500 BC, right? This scroll is approximately from, 1500 or so, a little right around 1,000 years ago, or a little less than 1,000 years ago. So that's an example of carbon-13 dating. I'm going to do one more problem here, looking at just a normal decay. In this particular example, it's asking us to find how long will it take 1.35 milligrams of plutonium-236 to decay to 0.1 milligrams if the half-life of this isotope is 2.86 years. So again, we're going to use our integrated rate law. We can use a ratio of amounts since we're given an initial amount and a final amount. Now, of course, before we get into this, we have to determine the rate constant, hence why the half-life is given to us. So let's do that first. So K will equal 0.693 divided by 2.86 years, which equals 0.2423 reciprocal years as our K value. So if we go back over here and we plug in here, so our Nit times T, right, is the 0.1 milligrams. And so as long as we have the same units here, it doesn't matter if they're milligrams, grams, because the units are going to cancel, right? It's just the ratio that's important. And our initial was 1.35 milligrams equals negative 0.2423 reciprocal years times T. So if we start to do our math, right, we get the natural log of 0.1 divided by 1.35. So the natural log of 0.07407, let's just say, for equals and then if we rationalize that, we get the natural log of 0.07407 is going to equal negative 2.6027. And then we can solve for t by taking our negative 2.6027 divided by negative 0.2423 reciprocal years. And what we see is that we do that, negative 2.6027 divided by negative 0.2423 equals 10.74 years equals t. So it's going to take about 10 3/4 years for this sample of plutonium, this very tiny sample of plutonium, to decay down to where there's only 1/10 of a milligram left. So, same basic types of problems. You can have this in a lot of different ways, a lot of different examples. Now, I will alert you to a couple things that will sometimes happen, is that sometimes they will give you problems where they're trying to sort of test your understanding. So if you see problems like, how long will it take a sample to drop to 25% of the original sample, or 12.5% of the original sample, right? What they're trying to get you to understand is the constant half-life idea, right? You don't need to do any math to do that if you know the half-life, and typically they'll give you the half-life in these kinds of problems. Then we understand that dropping to 25% means 2 half-lives. So twice the half-life would tell me how long that took. And so it can do that very simply without actually doing any of this more lengthy math. And so sometimes even with problems given like this, right, if there's, if they're giving you the initial amount and the final amount, and it's half or 25%, or, a nice where you can sort of glance at it and say, oh, if I look at the half-life, that's 2 half-lives or 3 half-lives. So sometimes problems are done in such a way that you can rely on the half-life to get to a very accurate age. Now, you don't want to be trying to do this with something like this that's going to be, you want it to be a nice even number of half-lives. Otherwise, just go ahead and do the math. It's not hard math. That'll get you a more accurate number.